Right, and welcome to this lesson on, we're going to be doing complex ions, and hopefully we'll finish then the the Chemistry 3061 booklet within half an hour, and then we'll go and do some problems. Did you manage to look at those videos that I sent you for Science Scribe? It doesn't matter if you haven't, but I just want to check, because I just want to see if a sort of a flipped classroom. Okay, you didn't. Fine. So we'll do it from scratch. Okay, just to revise Le Chatelier, you do need to know Le Chatelier for all parts of this exam or this content. So remember what Le Chatelier's principle is when my system is in equilibrium, then I've got an equal rate of reaction going forward and back. But when I put a stress into that equilibrium so that it's not an equilibrium anymore, I might have changed my temperature, changed my concentration, added something, taken something away, any change to that equilibrium. So when I say stress, I mean there's a change. So in this case, okay, here I've had my silver chloride in equilibrium with the dissolved chloride and silver ions, and I've just made up a Ks value because remember Ks is the concentration of your products, so it's equal to 4. Now if I add a stress, or change, in this case my change is adding silver ions, it's not an equilibrium anymore. If I try to work out my Ks, it's now going to be an IP. Remember my ionic product, or my Q value. You'll see it's 1, 2, 3, 4, 5. 5 times 2 is 10. So my ionic product has been increased. So there's a stress, so my equilibrium has to shift. The position has to shift in such a way as to remove that change. So here I've added silver ions aqueous, so I've got to remove silver ions aqueous. And the only way I can do it is by precipitating them out. So remember when we talked about IP last time, or Q, whichever way you want to use it, but if your ionic product is bigger than your Ks, it's going to shift towards the left because you want to get rid of products, because you want to get your ionic product to become equal to your Ks, so this has to decrease. So it shifts to the left, and so we do that by removing some silver and some chloride. So silver ion and a chloride ion goes across, and it's now in equilibrium again because the Ks is equal to 4. So is that sort of quite clear in your mind how this principle works? Right. Okay. And then we'll just flick through that. Now, we can change the solubility through your stress, or put a change in. There is a temperature one, but the common ones they talk about, and you have to explain, is the common ion. So that's what we've just done. We added silver ions to our silver chloride solution. Complex ions, and these you do have to learn off by heart, and then the pH. A pH will affect any salt or system that is affected by either hydrogen ions or hydroxide ions. So for example, if you have a carbonate, silver carbonate, what do you know about any carbonate? Are they acidic, are they basic, or are they neutral? They're basic. So if I have silver carbonate and I add acid, although I'm not adding a common ion as such, the acid is going to react with the carbonate, and so it will change my solubility. Straightforward common ions, if I say had iron hydroxide, by adding a base like hydroxide, that's changing the pH, but I'm obviously adding the common ion, OH. Right. Now, let's go to the complex ions, because these are the ones you must learn off by heart. And as I said last time, remember Zec and Zelp. So Zec is zinc and silver and copper. So there's Zec, zinc, silver, copper. and I've sort of coloured him blue because he's ammonia, and ammonia has round about a pH of 10, depending on the concentration, of course. So these are the ions or the metals that form complex ions with with ammonia. And by forming complex ions, they may become soluble. Okay, to see you typing there. So if I had, say, an insoluble zinc salt, right, they're all transition metals, yes. Iron, there are a number, but these are the ones you definitely have to know. Lead over here is not a transition metal, but it is one of the heavy metals. So if you have, for instance, zinc carbonate, it's insoluble. If I add ammonia to it, even forgetting that ammonia is a base, so we'll just ignore the pH bit, but ammonia will complex the zinc and will so it'll remove any zinc ions to form a complex with it. So that is my change. I'm removing now products, so I'm going to make something more and more soluble, and we'll see it in equations just now. The same thing with silver and copper. Then hydroxide does the same thing. It forms a complex with zinc, aluminium, and lead. So I made it ZELP, so the Al stands for aluminium, but the L also is to help you for the lead. So for the P is the beginning of lead, but the, because it doesn't have the same letter, P, lead, at least the L will remind you of that. And as a tip, they all form 4 ligands, or four of those ions latch around the metal ion, except for the silver ammonia complex, which is 2. So that's one way of remembering these. So what I'm going to show here very quickly is copper, and I'm adding ammonia. Can you see I'm getting a white hydroxide being formed? Okay, so I'm going to actually stop it there before it carries on. I'm getting that white hydroxide being formed because ammonia is basic. So my copper ions is going to react with those basic OH ions. So before it even starts with the ammonia, it's going to react with those OH ions, and I'm going to get an insoluble copper hydroxide solid being formed. So if I take it back a bit, can you see it's gone all cloudy? And that's that white precipitate of copper hydroxide being formed. Now I keep on adding more ammonia, and I carry on adding more ammonia, and I'm going to stop it soon. It doesn't look quite transparent yet, but I don't want to get it too far. But I hope you can see it's starting to become transparent. And what has happened, as I add more ammonia, the ammonia takes any copper ions, attaches 4 ammonia molecules around it. Those are called ligands. It uses the lone pair on the nitrogen to do that. And that whole complex is soluble. So if I had any copper hydroxide being formed, the ammonia attacks the copper, takes it away to form the complex. So can you see my equilibrium is going to shift towards the left, towards the copper ions, and I'm going to start dissolving my copper hydroxide. Does that make sense? Yes, good. So whenever you add ammonia to copper ion, you'll first get that precipitate because you're forming the copper hydroxide, but then you form the copper ammonia, or copper amine complex. That's the proper name. Now this one is a little bit longer. It's about 2 minutes, but what they've done here is they're adding sodium hydroxide to the one, and they're going to add ammonia to the other. So I'm going, now they're just showing there the water complex, because copper isn't just sitting by itself on the water. It's also got ligands around it. They're just water molecules, and that's what makes it pale blue. So can you see these at copper hydroxide being formed there? It's a very jelly-like. I actually said it was white. It did look sort of whitish, but sorry, it's actually a blue color. So if I move it on a bit, so there's a copper hydroxide being formed. Don't worry about your water over there. Now what they're doing is they're adding lots of, and I'm just going to stop it there. They've added lots of sodium hydroxide. Has my copper dissolved again? Do you still sort of see lumps on there? Okay, I think you're doing the yes. It actually hasn't. That's why I've put this YouTube Frankly Chemistry, so you can look it up yourself and you can look more carefully. I know it's not very clear here, but this is sort of transparent with the ammonia. Here, I don't know if you can see those sort of lumps. There's still lots of undissolved copper hydroxide, which shows that it's not the hydroxide that forms a complex ion. When I add hydroxide, it just forms a precipitate, and no matter how much hydroxide I form, the copper is going to not dissolve. So remember ZAC and ZELP. ZELP was for hydroxide. There's no copper in that ZELP name because copper does not form a soluble complex. Now if I carry on with this, and I'll move it. Yep, it will with ammonia, but not with hydroxide. Quite correct, Andrew. So let's go a little bit further. Okay, now they're adding, you can see there was a bit of hydroxide, but the solute, that sort of very deep color, you can, it's what we call a royal blue. Now they'll shake it up and you'll see it. Okay, can you see there's a precipitate? We've now mixed it all up, so all the copper has reacted with the hydroxide. It is a lighter blue than that, but it's still the copper hydroxide complex. And what they're going to do here is add lots of ammonia, and in that way you can actually really see this copper hydroxide sort of precipitating out a bit. And when that gets shaken up with the ammonia, we'll see it a lot more clearly. That it's transparent. Right, I'm just waiting for him to put it back. Okay, well that's I think close enough. So there's a precipitate, there's this precipitate. There you can see it's quite cloudy. It's sort of a very light pale blue precipitate there. But here it's transparent, you formed that complex. So as I say, you're welcome to do it yourself. Here Frankly Chemistry has done it with a lot of different ions, so I'm not going to go through it, but you're welcome to have a look, because seeing it will help you remember them, and because what he does, he tests them, and they aren't necessarily always soluble, so that you can see whether they do or not. Like, you know, copper does not form a soluble complex ion with sodium hydroxide. Similarly, you do the same thing with ammonia. He's done it over there. There's just an error in this one. He starts off with magnesium, but he actually talks about zinc. So you'll find this precipitate won't dissolve because it's actually, he's testing magnesium and not zinc. He does zinc later. As you can see, it's the third one that he tests. And then you'll see the zinc one will dissolve. Because zinc is in ZAC and in ZELP. It forms complexes with both. Right, so you think you'll be able to find those videos and have a look at them? Okay, I can send links out in my weekly email. Right, so here are the complex ions that you need to learn. So ZAC, remember, is the one with ammonia, and I've made this in blue to remind you of that royal blue color. And the zinc forms that complex as well, and notice they're always 4 ligands, but the silver is 2 ligands. Okay, only 2 ammonia molecules. And you can see from the charge, remember copper is 2+, you're adding a neutral molecule, 4 of them, but they're all neutral, so it's still got a 2+ charge. Zinc is zinc 2+, you're adding a neutral, so it's 2+ charge. Silver is Ag+, adding 2 neutral molecules, so it's still an overall plus charge. Remember, the square brackets mean a number of things in chemistry that you've come across. You know the square brackets mean concentration of. You know them in Lewis structures when you do draw Lewis structures for cations and anions. And you also use square brackets when you write complex ions. So that's 3 places you come across with square brackets. ZELP is with hydroxide, and notice they all 4 ligands attached. So the OH minus surrounds the zinc. There's 4 of them. Zinc is 2 positive. What is the charge on a hydroxide? It's there in case you can't remember. -1. So if I've got 2 positive surrounded by 4 negatives, my overall charge is 2 negative. Aluminium, what is the charge on an aluminium ion? 3 plus. So if I've got a 3 positive surrounded by 4 negatives, I've got an overall charge of -1. And then here lead, it's lead 2 positive surrounded by 4 negatives, an overall charge of 2 negatives. So do you think you'd be able to remember them as ZAC and ZELP and remember how to write these? Okay, right. So the last thing that'll affect the common ion, affect the equilibria and solubility is the pH. And again, any hydroxide is affected by the pH, because if I increase the pH, I'm increasing the OH minus concentration. So it's like adding a common ion. If I'm decreasing the pH, it's like adding H plus. And what do you think H plus will do to a hydroxide? It will neutralize it, so it'll react to form water, because H plus plus OH minus is makes water, and it means I am removing OH minus, so I am going to be shifting the equilibrium position because I've put a change into the system. And we will look at these sort of things in the next lesson, in this lesson, but in the second half. So we'll know what all that is. Right, and that's about it. And I think, oh, okay, here's a complex ion problem. So what it says here, this is from 2 years ago in the exam. I've got silver chromate in beaker A, and I've dissolved it in 50 mils. And in beaker B, I take the same silver chromate, but I dissolve it not in pure water, I dissolve it in an ammonia solution. So it says here, compare and contrast the solubility of silver chromate in beaker A and beaker B. No calculations necessary. So let's have a quick sort of overview. You got this insoluble silver chromate solid, and what you need to compare the solubility. So you think of, if you're comparing solubility, you've got to think of common ion, complex ion, pH. So am I adding a common ion here anyway? I've got silver chromate in water and silver chromate in ammonia. Is there a common ion? No. So the next one you've got to think of is complex ion, because this question is obviously we're talking about solubility and equilibrium shifts. Whenever you've got a question like this, is compare and contrast the solubility, we want to use Le Chatelier's principle. So do I form a complex ion in any of these? Yes. Now, in a way that video I showed with the water molecules going around the silver ions, don't worry about the water. We're going to ignore water as a ligand. Okay, so we don't get a complex ion with the silver chromate and water. Okay, but we will get, remember ZAC and ZELP, we will get a complex ion of silver with ammonia. So what you basically got to do is write the equations and refer to that particular equation when discussing the effect, and then show the equilibrium position shifting to the left or right for your equation. Now, so what I've got here is, here's my equation, my silver chromate, solid, always put in your states at level 3, in equilibrium with silver ions aqueous and chromate ions aqueous. Now, the other equation is forming the complex ion. So the silver ions react with 2 ammonia molecules to give me this complex. And now in your discussion, you can call this equation 1, and you can call that equation 2. So you can say what's going to happen in equation 2, the ammonia over here is going to react with the silver ions and turn it into a complex. Which means if the silver ions are going into this complex, I'm removing silver ions from equation 1. If I'm removing silver ions from equation 1, how is the equilibrium position going to shift in equation 1? Is it going to shift to go more to the left? I'm going to form more solid silver chromate, or is it going to shift to the right and I'm going to form more silver ions? It's going to shift to the right because it's got to try and replace those silver ions that I'm constantly removing to form the complex. So what you'll say in equation, you'll write those equations and you'll say the ammonia complexes with the silver to form a soluble silver complex, and you'll show that for excellence you must certainly be able to write that formula. And then you'll say in equation 1, because the silver ions are being removed, the equilibrium position will shift to the right, so I will have more silver chromate dissolving in solution. So when you're comparing and contrasting the solubility, you'll say that the silver chromate is more soluble in the ammonia because of the complex ion being formed. And then you'd have to refer to with Le Chatelier's principle and write those equations. Do you think you could do that? The hard part for most students is writing the equations. I find once students have written the equations, they don't actually have a problem. They can go for it. But students that don't write the equation will fluff around and get themselves so confused, or they may perhaps even know exactly what they mean, but the teacher doesn't have any idea what they mean because it sounds so confusing. So make sure you write your equations down, and then, as I say, if you've got more than one equation, call them equation 1 and equation 2 and talk about each one. What happens in each case is the equilibrium position shifting to the left and why, or to the right and why, and how does that affect the other equation. Okay, and then again, check that you've done all parts. So you've got to compare and contrast the solubility. So you can't just talk about the equations. You'll have to have a final statement to say that the silver chromate in ammonia is more soluble than the silver chromate in water, because you've got to explain the solubility in beaker A and beaker B. Right, here's another one. Discuss the effect of decreasing the pH of the water on the solubility of iron hydroxide. I know it's a 2012 exam, that's from the old standard. So when you've got a hydroxide and I'm decreasing the pH, if I decrease the pH, what am I doing? Adding H plus or adding OH minus? Adding H plus, correct. So first thing you do is whenever you've got an insoluble salt or insoluble compound, is you write this solubility equation. Okay, so always write that. We did that even with the silver one, the previous example. Now you do, just like we did with the complex ion in that previous example, now we do whatever the effect is. So what we're doing is we decreasing the pH. So we've got to talk about the H30+. And then its effect on my insoluble salt. So in the previous one, it was the ammonia on the copper. Now it's my H3O plus on my hydroxide. And can you see I've labeled this equation 1 and equation 2? So now we'll just say in a saturated solution, your iron hydroxide is in equilibrium with your Fe3 plus and 3OH minus. And if I decrease the pH, it's like adding hydronium ions. The hydronium ions react with the hydroxide ions. So it's as though I'm removing hydroxide ions from the solution because they're turning into water. And if that's happening, okay, so it's causing the equilibrium position. A lot of students, because you're writing so fast, you tend to say the equilibrium shifts. It's really the equilibrium position shifts. I know it's semantics, but it's try and be accurate. Shifts to the right, so more of the iron hydroxide dissolves, so it means it's more soluble. So discuss the effect on the solubility, it's more soluble. Okay, so that's another problem. Here's one from 2011 from the previous standard. So we've got zinc hydroxide, okay, and we've only got a tiny amount of solid zinc hydroxide in my saturated solution. So think of a beaker solution with a bit of white zinc hydroxide at the bottom. Now I'm increasing my pH. So how is the solubility going to be affected of my zinc hydroxide? So discuss what you, although it doesn't say it particularly clearly here, you have to talk about the Le Chateliers and so on, and you have to also talk about what you'd see as well. Now, Andrew, more precipitate, that is correct in the first instance. Why do you get more precipitate? Because remember, there are those three things you've always got to think of when you get questions like this. It's common iron, it's complex iron, and pH. And in this case, the common iron and the pH are sort of the same thing because it's a hydroxide. So why, you are correct, I will initially get more precipitate. Why? So if anybody's watching this recording, just think about what would all affect. You're adding more, well, be careful of saying adding more product, because our product is we've got our zinc hydroxide, and that's in solution with the zinc ions and hydroxide ions. So by increasing the pH, we're adding more OH minus ions. Okay, so that's what we're doing. So initially, I'm going to see more of a white precipitate being formed because of the common ion effect. And as I say, always write your equations first. There's my insoluble salt in equilibrium with its ions. And now I'm going to talk about, I've gone too fast, actually. So ignore equation 2 at the moment. So if I add a common ion of OH minus, then you would say, according to Le Chatelier's principle, if a change has been introduced, which is more OH minus, the equilibrium position shifts in such a direction to minimize that change, so the OH minus must be used up. So I'm going to get more solid zinc hydroxide being formed. But you also hopefully will remember ZAC and ZELP. Zinc comes in both of them, so that it comes in with the hydroxide. As I add more and more hydroxide, my zinc hydroxide is going to start forming a complex. Because initially I won't have much hydroxide, so it won't have enough hydroxides to form the complex. But as I'm adding more, it's going to form the complex ion. So what will then happen as I keep on adding, my hydroxide reacts with the zinc, so the zinc gets removed to form the complex, as well as my hydroxide, although don't talk about hydroxide because you're adding hydroxide, so that's constantly changing. The zinc has been fixed in my solution. I'm not adding or I'm not increasing or decreasing my zinc ions. They're fixed by the amount I added in the first place. By zinc ions, I mean whether it's in the solid or in the aqueous phase, that's fixed. So if I'm removing now the zinc ions to form the complex, then I'm going to get more zinc hydroxide dissolving. So it's a two-step thing. So you'd first talk about the equilibrium in the first place, then we change the system, so we add a stress, and so according to Le Chatelier we say which way it's going to go, and then we talk about so that's the extra OH, so we get more precipitate, and then we talk about the complex ion. Okay, and I think that's it. Oh no, I'm not going to go to this one, so I'm going to get out of here now. Whoops. Right, so what I'm going to do now is share my other screen. Right, sorry about that. Sorry. Swapping over midway. Can you see a FET simulation? Yes, okay. In 3062 and 3063, we're now going to be specifically talking about pH, acids and bases and everything relating to that. So 3061 were insoluble salts. Now it's acids, bases and salts that can be affected by acids and bases, or a salt that's formed between an acid and a base. So here in this FET animation we've got 5 different things. We've got straight water, and with water we've got the water molecules, a tiny number of them will break up to form hydronium ions and hydroxide ions. So when all these hundreds of water molecules, I'll show the solvent there, so these hundreds and hundreds of water molecules, as they collide with each other, very occasionally one of the water molecules will grab a hydrogen from another one. It'll break that covalent bond and to form the hydronium ion, leaving a hydroxide. And then that hydroxide will go and collide with something else, another water molecule, grab a hydrogen, and so on. So it's in equilibrium, 2 water molecules to every 1 hydrogen and hydroxide. There's only a tiny bit of this. So it's round about 0.0000001 of a mole. Okay? Water is about 55 moles per liter, so the amount of hydronium and hydroxide is tiny. As I said, 0.0000001. So there's not very much at all in water. So water is considered neutral. And it's also neutral because you've got equal amounts of hydronium ions and hydroxide ions. I think that's sort of very much sort of like the level 2. If I have a strong acid, so here's an example of a strong acid, and I can have that in there to show a pH. What do you know is a definition of a strong acid? It's fully dissociated. So if I had a strong acid of HA, which is this gray and a gray hydrogen, so there's my HA. What will happen if I put it into water? The hydrogen, the H plus, gets taken up with water to make a hydronium ion, and I'm left with the anion. It's fully dissociated. I have no HA in solution. So if I go first of all back to water and I show a graph, can you see there's my 55 moles per liter of water, and this is not to scale, but this is, I've got 1 times 10 to the minus 7 of hydronium ions and 1 times 10 to the minus 7 moles per liter of hydroxide ions. As I said, it's not really to scale. This is all a log. Well, this is like a log scale. If I have a strong acid, can you see I have no HA? We've called that negligible. Why they haven't said zero amount? Because at any moment in time there could be a collision between these two, but it immediately dissociates again. But we just simply ignore it. So there's no HA. I still have lots and lots of water. I mean, 55 moles per liter is an enormous amount. And can you see I've got equal amounts of the anion and the hydronium ion, because every one HA gives one anion and one hydronium ion. And I've got a lot more than last time. So my pH is 2, and it's showing me, because this is times 10 to the minus 2, I've actually got 1 times 10 to the minus 2 of hydronium ions, so 0.01 moles per liter of hydronium ions, and 0.01 moles per liter of the, sorry, that's the anion, that's the hydronium ions there. Okay, weak acid doesn't dissociate completely. So it depends on the weak acid how much it dissociates. So for some of them it'll only be 3% will dissociate, and others it'll be 50% will dissociate, others will be 75%, others will be 0.01%. It depends on the weak acid. So here's an example of one where it's most probably around about, I haven't worked it out, but probably between 3 and 10% dissociated. It's not very much at all, because it's remember the other one was times 10 to the minus 2, this is 3 times 10 to the minus 5, so it's quite a bit less dissociated. Now can you see I have got HA in solution, and I've still got my standard amount of water, that doesn't change, and I've got equal amounts of my anion and hydronium ions. But the trick to remember is I do have acid in solution, and I always have way more acid in solution than I have any released hydronium and hydronium ions and the anion, because my Ka is quite small. We don't deal with those difficult cases where Ka is sort of in between. We're always only going to be dealing with small Ka values. Notice I've said Ka. What do you think the A stands for Ka? Acid. Yep. So we're doing the equilibrium constant for an acid. So it's this equation of the products of A minus and hydronium ions multiplied together divided by the HA concentration. And water is a liquid, so just like with a solid salt we incorporated it into the Ks, we incorporate this water concentration, because it doesn't really change significantly anyway, we incorporate it into the Ka value. Okay, and we'll do those calculations next week. So that's the acids. If we do a strong base, so what they've done with a strong base is, remember a strong base is a metal cation, so like sodium hydroxide, so metal cation with a hydroxide, and it's, by being strong, it's fully dissociated. So I've got no sorry, I've gone blank. No strong base in my solution because it's fully dissociated. I noticed they haven't put the water in. It's because they didn't have water in the equation here. They didn't bother putting in the water, because it's not as though the water is reacting with this directly. And so I form equal amounts of the metal cation and the hydroxide ion. But a weak base does not dissociate completely. And here they've included the water because they've made the base react with water. They've made the base take a hydrogen ion from the water. Do you notice that? So it's gone to BH positive and it forms a hydroxide. So in a weak base I do have some of my base, and it's in bigger amounts than my products. So, and you'll notice the pH has gone up. Okay, but not if I look at the pH of the strong base, that's much higher. A weak base, it's lower, because I don't have as much hydroxide ion present. So do you get an idea of the species we have in solution? So by species, I mean this: my base, my water molecules, my base that's reacted with the water, and my hydroxide. Or for strong base, my species are my metal hydroxide, which I don't have present here, my metal ions, and my hydroxide ions. Is that clear that you can do those? That you can see that? Right. Okay. So now I'm sorry, I'm going to share again to something different. It's that PDF that I'm having. So right. So I'm going to make this a little bit bigger. These are the aqueous species problems that you can get in the exam. So these are all from the past exam papers, and we'll work through some of them so you can see what we get. So, sorry, I just have to get this. And I'm going to change my color. There. Okay. So, whenever you get this sort of thing, what you need to check is it a strong acid? Whoops, I went slightly wrong there. Is it a strong acid? Is it a weak acid? Is it a weak base? Or is it a strong base? Those are the 4 things you look at. The other things you then look at is it a salt? I still haven't mastered how to write with these pens, so I hope that's supposed to spell salt. Okay, so is it a salt? And if it's a salt, you have to say, is it a salt of a strong acid, strong base, strong acid, weak base, and so on. But first of all, strong acid, strong base, weak acid, weak base. There are some acids you have to know off by heart, and they're actually given there. So those are HCl, HBr, nitric acid, and sulfuric acid. So if you get given any of those, or a sulfate, or a salt of any of those, you are supposed to recognize it as part of a strong acid. So it's either strong acid or part of one. So just as an example, I'll put down the side here. If I had ammonium, oh, this is really not working well. I thought I'd mastered this. If I had ammonium chloride, sorry, I hope you can recognize that that is ammonium chloride, NH4Cl. Is that, because a salt is always from a base and an acid. So what did that come from? A weak acid, strong base, or a strong base, weak acid, or a strong acid, weak base, or strong and strong? So ammonium chloride. HCl, right. So it comes from HCl, which is a, I'm going to make this a little bit bigger. Right, it's a strong acid, and NH3 is a weak base. Great, because as you can see, those are the ones you have to learn off by heart. Those are given, so those are the weak acids, and those are the weak bases. Now you might think, well, NH4, it's a weak acid over there, but remember it comes from the weak base. So if I have HCl here, the first thing they ask you, they do it stepwise for you, is write the equations for the reactions when they occur. So you need to recognize HCl is a strong acid. So hopefully you'd be able to write HCl. Oh, I think I'm going to go back to PowerPoints. I was hoping to be able to do this. Okay, it dissociates completely. Now, I'm deliberately doing something wrong, and I hope you can pick it up. So that's supposed to have been a positive charge, so that wasn't wrong. There's actually, you could say, two errors there. So did you pick up something I've done wrong there? Okay, I don't need the brackets for ionic because they're not needed. I mean, I don't say like I've got, you know, if I've got, say, 2 hydronium ions, I put the 2 in front or anything like that. I have not put in states, correct, and I should put in states. Okay, and the other thing is it balanced? No. So make sure, and that's why they said when it's added to water, and they've said for the reactions. So what I should have done is, I'm going to try and write a bit better. Oh, HCl, I've got to say plus H2O. And I'm not going to spend time with the states simply because I'm struggling here a bit. But can you see you must put in the water? Okay, so if you put in the water, then it would be balanced, but also make the states. Now, this over here, let's go to a different color. That, as I say, these are the ones you simply have to learn off by heart. If you remember from your organic, that's an amine. And amines are basic, and you also expected to know this amine for this standard. So it's something that's basic, and it is a weak base. So how do you think it's going to react with water? You can perhaps type it as well over there. Now I'm going to assume there are states put in. So this is going to be a liquid. Okay, so say L for liquid plus water. Okay, it's going to steal a proton, so it's going to steal a hydrogen ion. And so I'm going to have CH3. I have great respect for people that can just write and have them. I get it better if it's faster. So it's CH3 positive plus OH minus. This is not easy at all. Correct, you're really there ahead of me. I think it might be easier just to type it on, quite frankly. I might actually try and do that. So ammonium chloride now, that's the next one. What is ammonium chloride? Is it a base, or is it an acid, or is it a salt? It's a salt. And as we said in that green earlier on, it's from the strong acid HCl and the weak base ammonia. So is it a soluble salt? Yes, because remember your solubility rules, GRAN, group 1 ammonium and nitrates, they're all soluble. So what this does, when I put ammonium chloride in water, then I'm going to make there's a 4 missing over there. So it says it writes for the reactions occurring. I must admit, I would put 2 things in here, because the first step is this. it dissociates completely Yo, have you ever used one of these things? So it dissociates completely to that and Cl minus. Okay. Will my Cl minus react with water? No. Because it comes from a strong acid, it doesn't react with water. I'm just going to flip over here. But what will happen is my ammonium ion, being a weak acid, sorry, I'm going to go down again. Do you remember up here we talked about that it's a weak acid, my ammonium ion. Whoops, I've got to get back to my color. Do weak acids react with water? Okay, you're not. Yes, it does. So just like my weak base reacted with water over there, a weak acid also will react with water. And I'm going to see if I can just type in, because that's going to be just so much easier. So if I just type in over here, what I'm just going to have is NH for, it doesn't do superscripts and subscripts, sorry, plus H2O, and please ignore the superscripts and subscripts, and I'm going to get formed NH. If it's acting as a weak acid, remember it's got to donate a proton, so it's going to form NH3 plus H3O plus. Okay, I think, is that clearer to see even though there's no superscripts and subscripts than my horrible writing? Oh, right. And now I notice, okay, so I'm learning. So I'm just moving that up so hopefully you can see it. Okay, right. I'm learning about this. Now, so the NH4 positive, remember it's a weak acid, so it donates a proton. So will my solution be acidic or basic? Acidic. Correct. So that's like a double check. So if you've got a salt of a strong acid, weak base, then you're going to have an acidic solution. So you must always have some hydronium ions showing there and not hydroxide ions. So if you've made a mistake in that calculation, then in that equation, that's one way of picking it up. Okay, right, we're going through a little bit slowly. So let's go here. So it says here, for each of the following, list all the species in order of decreasing concentration. So if I now write these in, it says do not include water. What will be present in the most concentration? And if there's two that are in equal concentration that are most, just give them both. Yep. So in other words, when I put my HCl in water, what species have I got? Okay, I don't have any HCl. All my HCl, the moment I put in water, breaks up. So you can't have HCl present. So can you see there, what I've got there is, whoops, just trying to move it over there. what I've got present is H plus ions and chloride ions, like I tried to show with that PhET diagram. So do you have any other species in solution? No, you don't from the HCl. Quite correct. So when I put HCl into the water, I get equal amounts of H plus and chloride ions. I do have, though, one other species in solution, and that was in that very first PhET diagram I showed you. Remember when I showed you water? Water existed as 55 moles per liter of H2O, but there was this tiny amount of what? OH minus. So there's a tiny amount of hydronium ions and a tiny amount of hydroxide ions. And that's always going to be there. So you do need to include that as well. So when we have HCl and water and they tell you ignore the water, they just mean ignore the H2O. Don't ignore anything that comes from the water. So you will need to say then, and I'm just going to include it to something else, that is going to be much more than the OH minus. Okay, so I hope that's, you would list it pretty much like that. So it's HCl, you could say HCl equal to the chloride ions. Ideally, as a matter of interest, I could write that more correctly by putting square brackets around those species, because I've asked about a concentration. But I don't think that'd mark you down if you said H plus. This should actually, I think, be better if you said equal to. Which is much more than the hydroxide. Okay. What about the CH3NH2? So if I go up here, okay, that wasn't very clear, so let's just go down and we'll do it again. So remember what we had the methyl amine, or methanamine if you want the organic name. So it's CH3NH2. Now that dissociates, remember, in the water, and it reacts with the water, and it acts as a base, so it's going to accept a proton. Sorry. And sorry, I've written the wrong thing here. You can't see it yet, but anyway. Right, hopefully you can see it there. I'm just moving it over. Right, so you've got correct, so it's a CHNH2, that's the one that's in most, because that's, remember, only some of it dissociates. And forget I've got 2 3s in there, so forget about that one. Let me just correct that quickly. Okay, so I've got that positive, and then I've got equal amounts of OH minus, and quite correct, then I've got a tiny amount of hydronium ions. So that would come up next. Now, do you want to, just before we finish, do that very last one, NH4Cl, just while I quickly do. So you typing in there, and I'm going to type, we'll race and see how much we've got. I definitely think I'm going to go PowerPoints next time. So you've got that, you've got the, right, you've got some CL minus. Can you try and do it in an order of most to least and see what you get? So I'll just bring this in properly. Okay, yep, you're getting it there. Right, so what I've got there is my ammonium chloride's going to break up to form chloride ions and ammonium ions. Then my ammonium ion, a tiny amount, so little that I can actually say the chloride and ammonium is the same, but a tiny amount will react with the water to form ammonia and hydronium ions. And then, of course, from the water, I'm going to have the hydroxide. Yep, so you've got it NH4Cl, that's correct. Always put equals or bigger than, so we know, that it's not all the same. And, yep, the hydroxide is, of course, the smallest one, because ammonium chloride is a acidic salt. Okay, we're going to stop there. How do you prefer to sort of going through problems like this or having a PowerPoint? Problems are okay. Okay, I'll see if I can master it to do better writing. Right, so next week we'll be doing some acid-base problems and titrations, and hopefully I do want to fit in 2 revisions before the exam, so I'm just going to check that out because I wanted to go over the organic paper and over, organic papers, not the practice exam paper. Yep, you can learn more by practicing, that's correct. Okay, right, so you have a good week. Right, bye.